Okay, now it's time to move on to angular momentum. We already have seen linear momentum when we said that linear momentum was defined as p, which was a vector, as m times v. So that was the linear momentum, and we said that according to Newton's law, second law, the rate of change of linear momentum was equal to the resultant of the force applied. And we also said that if equals 0, which means the net force acting on the system is 0, then P is a constant, which means momentum was conserved. Alright, now we have already drawn analogies between translational and rotational system, so we can certainly draw analogy here also. Okay, similar to P, there is something called angular momentum, which is expressed as letter L sometimes, or capital L, and is expressed as, you can see, m gets replaced by I and v gets replaced by omega, because we already have seen that this is what we write for angular system. If you remember this, the sum of torque equals I alpha. When we drew analogies with this, with Newton's second law, which said that, right? Remember? Okay, so this is corresponding to that. Similarly, we can say if the net torque is 0, then we can say I alpha equals 0. And if I alpha is 0, which can also be said that d omega over dt is 0, which means that I omega is a constant. Or you can say angular momentum is conserved. So if there is no net torque acting, then the angular momentum remains conserved. Similar to the case, if there is no force acting, then the net momentum remains conserved. So let's say you have something moving in with angular velocity omega, is hinged here, has a moment of inertia I, then we know angular momentum is going to be, which is a vector, omega I. You see, this is a vector, so angular momentum is a vector. Let me put alpha, arrows on everything. Okay, so this is the angular momentum. But if you do not apply any torque on it, let's say there is no friction present, it's an ideal situation. If you do not give any torque to the system is going to keep moving like this, keep rotating like this, and this term will always remain conserved. But if you apply a force such that it will provide a torque to the system, then what happens? You slow the system down and the angular momentum changes. That means you applied a torque. So when there is no torque present, angular momentum remains conserved. Also, angular momentum is not just for rotating bodies, that a body should keep rotating, only then it will have angular momentum. No, like for example, this is the definition for angular momentum. So whenever we have I present and whenever we have omega present, we know there is angular momentum. For example, let's say there is a particle which is moving in a straight line. So there is this particle moving in a straight line with the velocity v, and let's say this is your origin. So you can always define angular momentum with respect to the origin. So let's say if the radius or the distance from the origin is d, then you know that v is given as r omega. So that means This guy at this point is rotating about this axis with an angular velocity v over d, right? Okay, but this is true only for this instant. This is only true about this instant, because when it moves here, you really cannot see the circle here. It does not mean that it's going to go in a circle. No, it's not going to go in a circle. But right here, right at this particular instant, you can sort of treat this guy moving in a circle at a distance d from the origin. So you can define an angular velocity omega, and this is all is being done just to calculate I omega. So you have omega. Also, you know that I is given as m d squared, because remember, this is how we calculated our moment of inertia. So this guy also has um, moment of inertia. This mass, this particle which is of mass m, also has moment of inertia about this point, because we remember moment of inertia depends on where do you choose your axis system. Torque does not depend where you choose your axis system in the z direction, but moment of inertia in 2 dimension depends where you choose your axis system. So your angular momentum L is going to be md squared multiplied by v over d, and that gives us mvd as the angular momentum. You see, because v is a vector, d is the distance here, this distance, the magnitude of the distance, the radial distance between the axis and the particle. So v is a vector, then that's why L is a vector. So this is the angular momentum for particle which is moving with the velocity v perpendicular to the line which is connecting the axis system and the particle. So this is an important formula. It's just a generalized, just a special case of I omega, and we'll solve one problem in the next lecture.